So where we left off yesterday was I got halfway through the section 9 of the lecture material. Today's your last day, so congratulations, you made it all the way to day 3. Start off finishing up a little bit of the material from yesterday still, conversion of sensitivity analysis to an error budget. Very first day I brought up that a lot of this effort is just the terminology. So once you've gone through the process of starting to collect data and look at the problem, now it becomes necessary to start putting numbers to and labels to some of these uncertainties. And so basically it's creating your error budget. And in this case what I did was, assuming that I'm having an at-sensor radiance prediction, picked out 5 boxes of topics that we would need to then have the uncertainties for, that would then get combined to then give me my total at-sensor uncertainty, both absolute and relative. And the ones that I chose here are surface reflectance, atmospheric parameterization, a couple of atmosphere and surface radiant transfer code, and test sensor digital counts. You'll notice this pretty much follows the topics of the material that we presented, and so there's no coincidence to both what's here and what has been shown. This is what drove a lot of that. Then the question becomes is, can you actually just sit down and say, well, the uncertainty because of this particular, let's say, test sensor digital counts, 3%. And how would you prove that? Well, then somebody would go, well, what causes it? What causes this uncertainty? And your next step is then to go into another layer and start breaking the surface reflectance up into, we know we have a panel measurement. So the bidirectional reflectance calibration of that panel. We're going to average a test set. That could be something that we have to worry about. The field spectrometer itself is causing uncertainties. And I can do that for all of these. I don't need to go through, but if you pick out the topic that you want, and I know that it's hard to read, and I do that on purpose. The idea is that there's more boxes here, and they're layered going down. So I went from having 4 or 5 boxes at kind of the second level to now I have a lot of boxes, and I can go even further. And I can add another layer. So now on the scattering effects, I'm adding molecular and aerosol. On absorptions, I'm adding gaseous and aerosols. And all of that, and this is just the 2 I picked out there. And I can go even further. And now it gets to be very hard to show this on a chart. And so you'll see this kind of trick play where I got my original chart up in the upper left, and I'm circling that one box, atmospheric parameterization, and now I'm layering out, and my molecular scattering now breaks up into atmospheric pressure and wavelength knowledge. Here is where you start to be able to say, okay, wavelength knowledge, I know that there's a lambda to the 4th dependency in molecular, but I know I'm going to know my wavelengths, and the wavelengths that I have, this is trivial. That gives you an idea that now you can assign a number that you're happy with, and especially if it's a very small number. There's no reason for you to break this box out any further. If you have a 0.1% here, and you have a 4% up there, this may be where you want to look for your, the story I tell people is, there's a joke of somebody, I walk out of the grocery store, and it's at night, and into the parking lot, and there's a person that's crawling around on the ground. And I walk up to them, I go, what's the problem? Oh, I lost my car keys. I go, oh, well, you want some help looking for them? And they say, oh, yes, that would be wonderful. So I get down on my hands and knees and I start crawling around looking for the keys as well. And after an hour of searching, I finally just go, you know, we've covered this whole area around here where you think you lost the keys. Is this really where you think you dropped them? Well, no, I dropped them over there. Well, why are we looking for them here? Because this is where the light is. It's easier to look here than it is over there. So the real problem's over there. The real problem might be in absorption effects. The easy one is down here at wavelength knowledge, and you can just keep going from 0.1 to 0.01 to 0.001, and it's not going to help you find your car keys. The other analogy is the chain link, and it's the weakest link in the chain that always causes the problems. That's what you want to fix. I just like the visual thing of me crawling around on my hands and knees and trying to find car keys. And all of these then, we get numbers that we want to assign to these. You have justifications. If we're doing it properly, then document that justification. You document those values. And then you start to combine them all up to go back to the original top layer. There's another way that this can be viewed, though. Traceability may be more important to you than the actual numbers. You may want to make sure that you have some methodology that's traceable to an SI standard, to a NIST standard, to some other NMI, whatever the standard is that you want. And in that case, they tend to follow kind of a arrow going all the way down to where what I want is my satellite sensor output comparison. So here's my sensor DNs compared to my at-sensor radians. And my starting point is the laboratory reflectance reference, recalibration of that. And up there in the tiny words, I have NIST traceable PTFE, and so I have my traceability starts up the upper left. I take that out into the field, so I have to now calibrate my field panel. And with that field panel, I make my spectrometer measurements. So there's now my traceability related to my field measurements that we've been talking about for reflectance. We also have to have some kind of atmospheric information. And I drew a line here to the atmospheric model, the rate of transfer code. That should make sense. I also have started drawing a line over here to the test site BRF. Because we might, and the BRF there is, we're not talking about bidirectional reflectance distribution function, the bidirectional reflectance factor. So I have good terminology here now. I'm not calling it reflectance as much as BRF. Maybe I want to correct for diffuse light now. And so I want to make sure that I have a means of getting atmospheric data in there, and I can see how that affects my traceability. So here's an input data set that I need to do my processing. It may influence my uncertainties, but it doesn't impact my traceability. It could break my traceability if I can show that by excluding this, these data here become not as valuable, and I cannot keep track of what their uncertainties are. But strictly speaking, my traceability path is following all the way down through this atmospheric model, up into band averaging, and out into the satellite sensor comparison to get to the answer. And if you're sitting there going, well, I would have done it this way, or I would have done it that way, that means you understand what's going on now. These are, the labeling is really arbitrary. The number of boxes that you come up with is really sort of arbitrary. There is no right answer to that. Where you can start having discussions is when you start assigning numbers. Somebody may say, I think you left this out. And then you go, no, I have a label that you do not quite understand. And so my label includes that. But just for clarity, I'll go ahead and now break it out into two separate boxes and relabel it. And it's in the communication process that we might start to iterate on the labels and the numbers and where they are and which comes first or which comes second. But if we don't start putting these down formally, we will never even get to them. To me, if we start arguing over the number of boxes and the labels in the boxes, that's normal science. That's not good. You know, to me, it's sort of distracting, but it's what scientists tend to do. At least there's something to complain about. And that's the first step, is we need to get to something that we can complain about. So then the absolute and relative, I'll bring this up again. In terms of the reflectance-based approach, I have just a few of them. But the absolute accuracy, we can be affected in some terms, and then the others will impact our relative uncertainty. So using the example we have here, the absolute uncertainty is affected by my surface reflectance. I can have a bias or a systematic error in my panel BRF. And so the goal that we're trying to get to is show that the error that we have in the panel bidirectional reflectance that we're using in the field, that's calibrated in the laboratory, that we know that that's more of a random uncertainty from time to time. We try to remove the systematic effects that are in the laboratory measurements as best we can, but they're going to remain because we know we have a 2% absolute uncertainty in the reflectance. That if I were to measure 95 times that panel reflectance, the true reflectance, I will never measure. I do not know what the true reflectance is, but my actual measured reflectance, plus or minus 2%, will encompass that true reflectance. And it could always be that same difference. It could always be, I could always be off by positive 1.8%. That's allowed. We get bothered. This is one of the things that really worries me and bothers me in discussions is I will go to a meeting and I will see a sensor A that shows a radiance, and I will see a sensor B that shows a slightly different radiance, and then everybody starts immediately talking about we should make them agree. Based on what? Just because they're different? Well, in reality, they are not different. They agree to within their uncertainties. Now, if you just want to make the picture look better, great, then let's have that discussion. Then we're not talking absolute, we're talking relative, I'm okay. But let's make sure we're talking about pretty pictures and we're not talking about absolute values. The phrase that we started using, we call them happy snaps. It's a click. In the old days, but nowadays, it's, at least when we have the camera, you can hear a click. So there's that snap of the picture, and if you get a nice picture, it makes you happy. It's a happy snap. So the systematic effects of sampling is another way that can hurt us. In terms of selection of the aerosol type, if I'm always assuming that I have a clean aerosol at a site that has some pollutants, I will always be off by a small amount of absorption. Always. So that's going to cause me to be biased. So what I'm going to get is I'm going to get some scatter, but that scatter will be shifted because I have too low absorption in my model relative to real life. The only way we find those out is if somebody else is making a similar measurement in a different place and they have an accurate error budget that we can then say these two instruments differ by more than their uncertainties. Error in the aerosol amount. Now what's nice is this one here creates a bias, but the advantage we have is it tends to be a random bias, and that's one of the good ones. So then what's tough is it gets usually tossed in as a relative uncertainty, but in reality it is a true absolute uncertainty that we're getting. It just happens to be a scatter. It's not a systematic one typically, because we periodically recalibrate the solar radiometer. Relative uncertainty, now we're talking about the repeatability of the surface reflectance. Field spectrometers, atmospheric influences, the stability of the aerosol. So I could make a mistake about the type of aerosol that I have, but if the aerosol never changes, I'll get really small scatter because of the aerosol type. And that might be okay. Especially if, again, we get multiple sites, we can start teasing out what's causing some of these effects and figure out most of the problems we have with reflectance base is because we're using the wrong atmospheric parameters. It's causing a systematic effect. And then the accuracy of the solar radiometer, which then feeds back up into the solar radiometer calibration, which then feeds up into the aerosol amount, which here is an absolute, down here it becomes a relative one. So if I'm constantly changing the calibration of the solar radiometer by 2 or 3%, now I'm going to get larger scatter. It may not be moving up and down because it's random, but most of us really don't like to see that big scatter about some data point. Combining them. In remote sensing, we have not done a very good job of knowing how to do this. And we have a really good excuse. Because remote sensing really got started in the 1960s, the type that we're talking about, the satellite-based type things. 1970s, it became more widespread. The 1980s, we started talking about doing global Earth remote sensing. 1990s, we had the launches of Terra with Aster and Lotus and Miser. And then 2000s, we had more launches. Now we're having the Sentinel missions. We really were just trying to figure out how to use a lot of really bad instruments to try and do really good work. We did not have time to start learning how, I would say, how to chew gum. And if you know what the gum is the guidance. And I never could figure out how to get gum out of guidance for evaluating and expressing the uncertainty of missed measurement results. So out of this whole expression, all they picked was guidelines, uncertainty, and measurement. But if you hear somebody talking about the gum, and you're talking about error budgets, this is the document. Now, right now, we're slowly starting to bring that into remote sensing. I have this reference up here. I want to make sure I point out and emphasize. And I'll say it twice just to make sure you get that I'm emphasizing it. This is just a document put together by a bunch of smart people at one institution on how to do the statistics of combining relative and absolute uncertainties. At some point, there's going to be another bunch of smart people that will look at this in a slightly different way and come up with a slightly different set of guidelines. And that will be wonderful. That will be good. The gum does not have to remain constant in time. So in that regard, we're constantly chewing the gum. We're constantly trying to modify it and make sure that we have some way to ensure that it still has its flavor and it still is, something we want to keep in our mouth and keep. People believe in true government anymore. I might be using a really bad analogy.
Yeah, I think they do.
But the whole idea is that this gives you, I do not want to have to learn all of the details. I know how to do a student t-test. I know how to do an f-test. I know about chi distributions and all these other, I at least can put that in a paper, and it'll usually help me get accepted in a peer-reviewed paper, even though I don't really do it. Okay, we're not paying that close attention yet. I've never done that. Every time I've said the student t-test shows, I have done the student t-test. I have done the statistics, the test of significance, and everything else. This is a very difficult document to read. Mm-hmm. Especially for someone like me, where I try to flip through, and I'm just looking for, I wish every author would do this. Here's the equation I want you to use for this. So I can skip by all the stuff, and here's the equation I need to use to combine relative and absolute uncertainties for vicarious calibration. Oh, there it is. I'm good. That is not, I've looked. That page is not in this document, unfortunately. We have to read it and understand it, and hopefully you can find somebody. I have access to people like Chris McClellan, and then at NASA Goddard, many people, Jim Butler. I have access to people at NIST who have lived this document, and so they've helped us figure it out. Now I'm working with the National Physical Laboratory people, Nigel Fox, and he's helping me a lot to get through this process so that we can combine these things appropriately, because some of these are systematic and or type B uncertainties, and some of them are random statistical fluctuations and or type A uncertainties, and they have to be combined to get our total type A and type B uncertainty. And I have come across a group on a project where they refuse to accept the GUM, and that's fine, because what they have opted to use are the terms systematic and random. And the GUM really does not allow you to look at that carefully. What it does, it allows you to look at the statistical fluctuations of a systematic effect and the statistical fluctuations of a random effect, but the actual systematic bias that you would get if you were off in calibration is not truly covered in this document. So the company that's building a system, they would rather keep those separate and careful. What they claim is, and they're correct, is the random uncertainty is really all that's covered in the guidance for uncertainty measurements. So back to our problem, and the reason I'm circling back is to demonstrate that we are still learning. This error budget, and what I showed is we break it up into bigger, smaller pieces, is nowhere near complete. It nowhere near follows the GUM. I have a bottom line number 2.5, I have a top line number 2.2, and one of the reasons I get away with this is because my dominant, all I really had to prove to myself is my dominant uncertainty is my reflectance. And once the dominant uncertainty is reflectance, we're talking about, we have a 2%, a 2.5%, a 3%. So if you put 2.5%, not many people are going to be worried whether it's 2.3, 2.7. Okay, that's there's a lot of assumptions that get rid of some of these terms. I'm using mid visible, I'm using no absorption. So it's a justifiable, defensible error budget. And it's a start. But the combination here is not following those guidelines yet, because this was developed far earlier than some of those things came about. So just to highlight again, in terms of the ground reflectance, this is the dominant error source. And what's nice is the dominant error there was done properly. And it was done following the guidance of how you do, the guidelines for how you do uncertainties and combine uncertainties. Because this was done in careful collaboration with the metrology lab. So we know this uncertainty is, if anything, it's very conservative. I think it's probably closer to 0.5 to 1%, but it cannot prove it. And we do not have the paperwork to prove it either. So we go with the 2%. No matter what I believe, belief is not in this. It's what you can prove. So the 2% is something that's there. This 1%, well, we can argue whether that should be 1, 1.5, 2, 2.5. But it then becomes more of a case of, can I get rid of the days for which this measurement error is larger or smaller? And I would never get rid of ones that are smaller, but if I know that I have a day where my measurement errors are larger, there's something in the ASD data that shows that something's wrong. I will take those out. I will remove them. A cloudy day will not be included in the processing scheme. A day where the panel is known to have been tilted. A day where somebody was known to have basically pointed the instrument up at the sky for half the data set. We'll remove that. And so this 1.0, if you go back and look at all my notes, you can tease that out on the good data sets. When I have 5 ASD measurements from a site, at the, and they basically cluster around a single value within plus or minus a percent. That's where this comes from. It still needs to be done a little bit better. We still need to understand the instruments. It doesn't impact, because I'm using RSS, it does not impact my total uncertainty that much. Even if I make this 2%, now I have 4 plus 4, I have 8. My uncertainty is still less than 3% total because of my reflectance. So what I really need to do is tell everybody that 2.5%, I have error bars on it. And it's a skewed error bar because we're pegged at the bottom. We can't go less than 0. So it's probably somewhere really between 2 and 3.2%. If we keep doing this training course, I suspect that these will get better, and the numbers will be more filled in. Some of them will get worse. Some of them will improve. Some of them will be better understood, and we'll have a better fidelity number to show. So maybe that'll be the reason that we have to keep doing this for the next 5 years. I'll have to keep improving the actual error budget to keep coming back. Absorption computation. So we talked about this. We know we have uncertainties in the absorption characteristics in terms of the amount of column absorbers in the atmosphere. All I'm going to do is pick a wavelength where they don't matter. That's legitimate. Now, if somebody comes back to me and says, oh, by the way, we need you to do a calibration in the middle of the Chapuis ozone absorption band in the green part of the spectrum, now I have to go back and carefully add in this 2% uncertainty in column ozone and what the impact would be at the top of atmosphere radiance. The aerosol type, and this again goes back to what I was saying, is right now we're picking a value for the index of refraction, and based on the literature, we know what the variability is of that index, so we have documentation for this 100% error in complex index. We have a number for that because luckily we picked White Sands missile range, and for whatever reason there was somebody in the military, well, we know why, but there was someone in the military who was very interested in what the particles looked like at White Sands, so they did a chemical analysis of most of the airborne particles. So we have the complex index as measured, and we have an uncertainty for it. Put that into the rate of transfer code to do a sensitivity analysis, and that gives us an idea of what the absolute uncertainty could be because of that parameter. That's a really well done uncertainty. This 0.3, well, the Yuga parameter itself, we have to go back and redo this one at some point because I have correlated errors that are tucked in there because of the fact that we're making measurements as a function of wavelength to retrieve that size distribution. And that's going to change depending upon where my uncertainties are in my solar radiometer. So I really need to do an analysis of what are my true instrument uncertainties going into the measurements that give me the optimal depths that go into the Yuga parameter. I will be surprised if it changes dramatically from this because this matches what the Aeronet team is coming up with as well. So again, we have literature that we can point to give us some confidence in those numbers. So a little bit of history, those things I just showed you, and that big table that we've been going through a couple of times, put together in 1985 is where the first one was. And the listing, so my list, as I go forward, is going to change. So I have those blue boxes that I showed at the very beginning, is what I'm starting to do to create a new error budget, because the error budget that was created by the original remote sensing group at Arizona was not done by atmospheric scientists or surface people. They were done by optical engineers, and they labeled things in ways I do not like. So if you go back to 1985, that's where they started. In the mid-90s, they brought in new instrumentation, and so then they revised some of the numbers. In the early 2000s, I got involved, and I improved our understanding of the atmospheric effects, because that's what my background was. And basically, we ended up with some better numbers there. The big thing that happened was, in the late 90s, NASA started the Earth Observing System, Terra, Aqua, Aura, and then some of the follow-on missions. Within that was a recognition that calibration played a key role. So they forced the NASA scientists to start talking to the scientists at the National Institute of Standards and Technology. We brought the meteorological community, not the meteorological community, the meteorological community into the discussion. And they forced us to start doing better error budgets. ESA, frankly, right now is doing a much better job than NASA ever did in forcing their scientists to start doing better error budgets. The Sentinel program is just kicking it to the next level in terms of with their fiducial measurements and things like that. And the push for the essential climate variables that ESA is pushing for, the United States is pushing for it as well. China is active in trying to work towards these climate variables. That is going to force us to have better traceability. And that's going to force us to go back and forth between the NMIs, the meteorological institutes, and the scientists. So we basically need to now take the vicarious calibration and redo the relative and absolute uncertainty analysis. And so one way to look at it is everything I showed you here is wrong. All of the numbers that I presented, all of the values that I assigned are wrong. And one way to look at science is every answer you give in science is always wrong. And that's not the problem. The problem isn't whether it's right or wrong. The problem is how wrong is it? It's the size of the wrongness. And you can tell by, if you're an optimist, then it's how true is it. But technically, we can never tell what truth is. We do not know what the real answer is supposed to be. We have an idea of what wrong answers really look like. And so that's why I tend to go from the side of, that's really wrong. This one's not as wrong as that one, so that's a little bit better. And that's where accuracy, because accuracy is a qualitative. So this one's more accurate than that one. Well, now I need an uncertainty. Well, the absolute uncertainty of this one is 0.2% and this one is 0.8%. My algorithm needs 0.01%. Okay, now we need to have a discussion as to whether remote sensing is the best way to do this. And that's only happening if we get these error budgets properly.